Hey everyone, and welcome. Today, we're going to dive into something that's basically the secret engine behind almost everything, mathematical logic. It's the set of rules that powers clear thinking, from writing computer code to just, winning an argument. So let's jump right in. All right, let me start by asking you a quick question. Just think about this sentence for a second. Do your homework. Now, can you say if that's true or false? Seems simple enough, but the answer actually gets to the very heart of what logic is all about.
Yeah, it's kind of a trick question because the answer is neither. Do your homework isn't a statement of fact. It's a command. It's not declaring anything, so there's no way for it to be true or false. And that little distinction, that's exactly where we start.
So in the world of logic, everything is built on this one core idea, something called a statement. You might also hear it called a proposition. All it is a sentence that makes a claim. It declares that something is a certain way. And, this is the important part, that claim has to be either 100% true or 100% false, no in between. So, for example, the capital of Virginia is Richmond. That's a perfect statement, right? You can check it, it's verifiably true, end of story. But then look at this other one. X is an even number. Is that true or false? Well, who knows? It totally depends on what X is. If X is 4, it's true. If X is 7, it's false. Since its truth value can change, it's not a statement.
So here's our game plan. We've just covered the absolute foundation. Next, we'll see how to connect these statements together. Then we'll bust out a really powerful tool called the truth table. We'll also tackle that kind of tricky if-then promise. And finally, we'll see where all this logic stuff actually shows up in your day-to-day life.
Okay, so we've got our basic building block, the statement. We know what it is. Now we can get to the fun part. How do we combine these little Lego bricks of logic to build something bigger and more complex?
Well, to do that, we use these special tools called logical connectives. You can think of them like the grammar of logic. They're words like and, or, and not, and they let us link up simple statements to make much more interesting ones.
Let's start with conjunction, but honestly, you probably just know it as and. Now, the and connective is a really strict gatekeeper. When you link two statements with and, the new combined statement is only true if every single one of its parts is true. If even one little piece is false, the whole thing falls apart.
And we use this constantly without even thinking about it. To be ready for the beach, you need sunscreen and a hat. Not one or the other, both. To create a diamond, you need intense heat and intense pressure. Again, both are required. It's a package deal.
Okay, now this is a truth table. Think of it as a cheat sheet for logic. It shows us every possible outcome. P and Q here are just our two simple statements. And just look at that final column. Notice how P and Q is only true in that very first row, the one scenario where P is true and Q is true. Any other combination and the whole thing is false. All right, next up is disjunction, or as we usually say, R. Now, R is way more laid back than and. A statement connected by R is true as long as at least one of its parts is true. The only possible way for an R statement to be false is if every single piece of it is false. You see this all the time with choices, right? A forecast might say tomorrow will be sunny or rainy. If it turns out to be sunny, the forecast was right. If it turns out to be rainy, the forecast was also right. It's flexible. You can take a bus or a train to get there.
And you can really see that flexibility when you compare this to the AND table. Look here. P or Q is true in 3 out of the 4 possibilities. It only fails in that one single case at the bottom where both P and Q are false. See the difference? Much more forgiving.
So the simplest connective is actually one called negation, or just not. It doesn't even combine statements, it just acts on a single one, and all it does is flip its truth value. It's a truth inverter. If a statement is true, putting not in front of it makes it false, and if it's false, not makes it true. And yeah, the truth table for this is about as simple as it gets. If P is true, not P is false. If P is false, not P is true. That's it. Simple as that. So we've been using them, but let's officially put the spotlight on our most powerful tool here, the truth table. This is our ultimate guide. It lets us map out every single possibility for any logical statement, no matter how complicated it gets, and figure out its truth value with zero guesswork. And building one is a really simple 4-step process. First, you just figure out what your basic statements are, your P's and your Q's. Second, you just list out every single possible mix of true and false for them. Then, step 3, you just apply the rule for whatever connective you're using, like AND or. And finally, you get your final output for each and every row.
Okay, let's move on to our next connective. And this one can be a little bit tricky, but it's also one of the most powerful. It's the if-then statement. In logic, we call it an implication. And the best way to think about it is as a kind of promise.
So let's use a really simple promise to wrap our heads around this. If it is raining, then I will bring an umbrella. The "it is raining" part is our condition. That's the if. The "I will bring an umbrella" part is the result. That's the then. And the truth of this whole sentence depends entirely on whether I keep or break that promise. Okay, let's really walk through this truth table. Top row, it's raining, and I bring my umbrella. Did I keep my promise? Yes, so the statement is true. Second row, it's raining, but I don't bring my umbrella. I broke my promise, so the statement is false. Now, here's the weird part. Look at the last 2 rows. In both cases, it is not raining. This is the key takeaway for if-then statements. A promise is only broken, the statement is only false, when the if part happens, but the then part doesn't. If it doesn't rain, my promise was never even tested. So whether I bring an umbrella or not doesn't matter. I haven't broken my word. That's why the statement is considered true in both of those last 2 cases. It's a bit strange, but that's the rule. Now, I know this can feel a bit abstract, like we're just playing with letters and tables, but the truth is, these rules, these connectives and truth tables, they are literally running the modern world. It's not an exaggeration.
I mean, seriously, where is this stuff? Every single time a programmer writes an if statement in their code, they are using implication. The tiny circuits inside your phone and computer are built from physical versions of and, or, and not gates. When a lawyer or a philosopher builds a case, what they're doing is creating a long chain of logical statements. This is the language of structure and reason itself.
So I want to leave you with this to think about. Now that you've got the basic tools for clear, structured reasoning, start looking for it out in the wild. Where do you see flawed logic? Maybe in advertisements or in arguments you see online. Because just being able to recognize it is the very first step to thinking more clearly yourself.